This year, we decided to replace our previous rocker bogie suspension with something atypical but quite performant, tank treads. Each track is made from two roller chains wrapped around a set of pulleys in a trapezoidal arrangement, bridged across with 200 3D printed flexible TPU teeth. TPU was chosen for the teeth after noting how rigid teeth fail to maintain traction on certain surfaces. Custom pulley rods with skateboard bearings and 3D printed sheaths keep the chains free rolling while also holding together each tread body. The side plate geometry gives the suspension plenty of rigidity and has several holes for design experimentation. The treads are driven by a sprocket rod with high torque closed loop BLDC motors coupled with 100-to-1 gearboxes. In our testing, the tank treads have outperformed all of our wheel designs due to the huge contact area with the ground, as well as the ability of the treads to float on loose particulate and climb over obstacles.
Our arm is a 6 degree of freedom belt and gear-driven system. The two main joints of the arm are driven by 3 kilowatt brushless motors with closed-loop motor controllers. The choice of precision gearboxes and steel-reinforced belts allow for an arm that has extremely low backlash in comparison to other drive methods. The belts also allow us to keep the large mass of a motor and gearbox off the linkages of the arm. The high power rating of the motors allow for an extremely responsive system and ensures that the arm is never operating anywhere near its limits during the competition. The arm also has enough power to lift the rover and push it in the very unlikely event the rover finds itself to be stuck. A differential wrist mounted atop a rotational axis provides 3 axes of rotation in a compact yet capable package. Our custom lead screw-driven gripper with TPU grips has proven to be strong, lightweight, and reliable.
The main backend of our rover is powered by ROS2, making use of its data distribution service over our 2.4 GHz Ubiquity rockets. A 5 dBi omnidirectional antenna on the rover is coupled with a 5 dBi sector antenna on the base station. We have gotten 5 megabits per second at a distance of 1 kilometer, which is enough bandwidth for the bare minimum controls.
On board the rover is our custom-designed power management system. This system watches out for overvoltage, undervoltage, or large deviations in any onboard battery cells. This system has control over the main power relay for all the actuators on the rover, allowing it to cut power if it detects any irregularities. The system also has a physical stop on board the rover to cut power in the event of a malfunction. This system is watching over a pair of 6S 22.2 volt 9 amp hour lithium polymer batteries that have the proven capability to run our rover for nearly 2 times the competition time. The system also controls an LCD on board the rover to display critical information and error codes if something is malfunctioning.
The rover's base station contains a dual monitor setup, dual 3-axis joystick for arm control, and a PlayStation 5 controller for driving and other miscellaneous controls. To make the base station as mobile as possible, all power supplies were replaced with custom voltage regulators to allow the whole system to be battery powered. Included with the rover's power system is a remote with an LCD, an e-stop button, and 4 macro buttons. Using a bidirectional heartbeat, the power system can automatically cut power to the motors with a signal loss. This system was designed with safety in mind but can be overridden for events where power loss cannot be afforded. 4-camera live streams with dynamic frame rate quality are available for the operator to view as they complete the missions.
This year, with our switch to ROS2 Humble, we're making use of the capable Nav2 stack. Using a stereo camera, we're able to generate a 3D map of the area around the rover. This 3D voxel map is then piped through a tunable algorithm that decides, based on various thresholds, which part of the 3D map should be marked as an impassable obstacle, obstacles that should be avoided if possible, and safe spaces to traverse. Precise global positioning of the rover is made possible using real-time kinematics, using dual GPS modules. Using MapViz, we are able to see satellite imagery underneath the path plan and generated cost map to get a general idea of the area the rover will be traversing. Aruco markers are easily detectable through any of the onboard cameras on the rover. Our search algorithm begins with the navigation to the GPS coordinates. Once we have arrived, the rover will rotate on its point, hoping to pick up the Aruco marker in the distance. To detect the orange mallet, we are using a YOLO V7 model trained on several images. Using label IMG, we annotate each image used for the training of the model, which then finds the location in the image for the object. Then, using a depth estimation network, we compute the ROS transform and set that as a navigation goal.
We made a custom end effector that has a scoop and small temporary storage area. The scoop will dig down to the necessary 10 centimeter depth where it can then tilt up and store the soil into our temporary storage area behind it. Once the soil is there, we can turn the arm to the back of the rover where it deposits about 10 grams of dirt into a funnel. From the funnel, the soil is split into 2 main testing areas. On one side, we have a heating element, and on the other, a variety of organic compound sensors. After the tests are completed, the servo turns and seals the cuvette. We can then send this sealed cuvette to our judges.
Our science assays include a combination excitation/absorption spectrometer, multiple gas sensors, and a heating chamber. These gas sensors detect volatile organic compounds, methane, and other airborne indicators of life. The spectrometer will be searching for paranitrophenol, a product of combining paranitrophenol phosphate, various enzymes, and water. This results in a clear yellow indicator, which will show up easily in our spectrometer. The heating chamber is insulated from the rest of the rover and will reach temperatures of 400 degrees C, which will cause any organic material in the chamber to oxidize and can be detected by a sensor.